Rob Froney is KL7NA, along with Mark Priddy, Prid-D, KE7UFF, their paper on match filter and maximum A Posteriori Detector for amateur radio digital modes. Did I get that right? Close enough. All right, take it away, Rob.
Yeah, good afternoon, everyone. I'm glad you all came here. I'm a professor at Walla Walla University, and Mark is one of my students. He just graduated here this last June, and the spring quarter, just before that, we teach a digital or a communications class, and one of the things we do, of course, there is digital communications. And so we had a project, a class project, and the class project was to figure out how you can incorporate the information you have about the English language, or actually probably actually it would be more specifically the language that hams use on the air to make QSOs and digital modes, you know, things like QTH is whatever, you know, and Q is used actually quite a lot in that case, and of course the E and those kind of things. We know that some of those letters are more likely than others. And so we wanted to figure out, how do you incorporate that knowledge, the knowledge that some letters are more used than others, into a program such as FLDigi. And I'm a Linux guy, just like some of the rest of you guys. You know, we really appreciate open source software where you can look at the code, you can get in there and modify it yourself. And one of my goals, of course, was to try and help my students understand that they can get in there and they can get into their editor and they can find in the code where things do things that they like or don't like, and they can change them, you know? And so we wanted to do a real-world project. And so our idea was to try and figure out how to use these probabilities to do this. Now, this isn't something new, you know, it's actually, you know, this is theory that's known, but we hadn't figured it out, okay? And Mark here, he's, as I said, one of the students, and he was one of the students who did quite a bit of work on the software end of this, okay? One thing nice about being a professor is you can dream up cool things, and then you assign them to your students, and they build them for you. So Mark here, he's the whiz that spent all the time in the software. So what I want to do today is I want to give you a little mini class in how you would do this process. How does a digital communication system work? And then once you've kind of got the same theory that Mark got in the class, then Mark will show you a little bit about what he did and give you a demo of the software, okay? This is going to be a little bit more mathematical than the previous two talks. Okay, so what we're doing, this is called this kind of a detector is called a maximum a priori or a posteriori detector, and that comes from probability theory. We'll get into that in a little bit here. So let's look at, first of all, how does a digital communication system work in general? Here's a picture of a digital communication system. This light blue thing on the top here is the transmitter. And the transmitter is, in a digital communication system, the kind of communication system I'm thinking about would start out with text. You don't have to start out with text. It could be, you know, an analog signal or something like that. But for FLDigi, it starts out with text. It's you know, a text tool, a chat kind of a thing. And so you end up with a text stream that you start out with, and we need to map that text stream into ones and zeros. That's the first step. And we have kind of a little, I should say, academic kind of an example here, or a very simple example, where we're going to send the letter A and then the letter B. And we map that into a string of ones and zeros. And I'm going to suppose that the letter A was a 0, 0. That means A. And a 0, 1 means a B. And so what you want to do is you want to take that stream of bits, which is now a 0001. You can see that right here underneath, right there. That's the 0001. That represents the letter A and then the letter B, the 00 being the A and the 01 being the letter B. And we want to take those zeros and those ones and map those into a signal which you actually send out over the air, okay? And so you need a actual analog voltage that you can send out, put on your antenna and send out over the air. And so we will make the zero signal. We're going to use a frequency shift keying example here like you would use in radio teletype. And that's what we did basically all our experimental stuff with, was with RTTY. So we want to make the zero be a cosine wave of one frequency. You can kind of see that right here in the little picture. We have a little cosine wave with one cycle there for the period 0 to a t. Capital T would be the time when the first bit is done being sent. And then you can see there's another one here in the next period from t to 2t, and that's another little cosine wave there, just like the first zero. And so you put 3 of those little cosine waves in there for the first 3 zeros, and we'll make the 1 have a frequency that's twice as fast there. And you can see that 1 on the end kind of goes up and down really quickly, okay? So we're sending a low frequency signal for a 0 and a high frequency for a 1 in this example. And then what happens to that signal? Well, we put it on our antenna and it bounces off the ionosphere and somebody picks it up, who knows, in Argentina or something. So here we are, the guy in Argentina is listening to that signal, and of course he picked up that signal and he also picked up a bunch of noise. And it's all one on top of the other. And the problem for his receiver is then to try and take what he received and determine what we sent. And so in his receiver, which is on the bottom here, we have first problem he's got to do is he's got to synchronize his receiver with our transmitter in time. Now, the problem that he has is, when the signal was sent from here to there, there's a delay. And in reality, he generally doesn't know when we're going to send it. That's one of the things normally he doesn't know. He just hears something there, and he's not quite sure when it started or when it stopped. So he has what's known as a synchronization problem. His receiver has to synchronize in some way to our transmitter so that he can determine what we sent. And if you just kind of look at that graph that was received over here on the right, notice that there's a delay here. It's delayed by about half a period. And, it's fuzzy because of the noise on there. And so he's got the noise and he's got the signal there, and he's got to try and figure out what the clean signal looked like, which is actually to the left of the noisy signal there. And so, like I said, the first thing he's got is the synchronization problem. And then he has to figure out what in the world bits were sent by looking at those signals that he had coming in. And so you can kind of look at that signal yourself and kind of do that by your eyeball and figure out that, yeah, it was probably a 0001. But if it was a little more noisy, it might be a little more difficult. And so that's what the receiver has to do. And once he has the sequence that he thinks it is, a 0001, then he has to figure out what that meant. That 00 meant an A and a 01 meant a B. Let's go on to the next slide, which basically kind of elaborates the same thing again here. What we're doing is we're mapping the characters, which are the A's and the B's, the letters, into bits. And we're mapping the bits into signals, and the signals get sent and corrupted by noise, and then the receiver's task is to identify what signals were sent, map those signals back into the bits that they go to, and map those bits back into the characters. And in general, some of these processes in the receiver are easy and some are difficult. And what we're really concentrating on is the receiver in this whole situation, because we're trying to make FL-Digi receive better by using information that was not used in the previous incarnation of FL-Digi. And in general, if you are a receiver and you know something and you don't use that information that you have, you probably cannot receive a signal that is embedded with more noise, as well as if you use that information that you have to try and receive that signal. On the other hand, if you think you know something and you are wrong, and you use that information to try and decipher what came through, you are much more likely to get it wrong than right, okay? So you have to be careful what you know and be sure what you know before you really use it. So that's a caveat there. So that's what we're trying to do. And so let's look at this process in a little more detail now. And we're going to look at the last three things here, which are the receiver's job. And in general, the tricky part is identifying which signals were sent, which includes that synchronization problem. And mapping those bits back to the letters, that's very easy, and there's no problem in that. That's a very small amount of work on the software side. But the difficulty is trying to recognize those signals within the noise. And, of course, like I said, the synchronization issue is a difficult thing. And we discovered the synchronization part was probably, at least the amount of hours that were spent, most of it was in the synchronization. Now, let's look at, there's not just synchronization, there's synchronization as far as characters go, as well as synchronization as far as the bits go. And in my cheesy little example here, I chose to ignore the character synchronization issues, okay? If you look at this bit stream, 0001, and you just happen to start listening some arbitrary place in that bit stream, like maybe you turned on your radio just as the second bit was being sent, then you would get 00, and then you'd get a 1, right? And then maybe if you send another character after that, you'd get the first bit of the next character. And so you would be out of step or out of synchronization as far as the character went with what was being sent, and you would get garbage. You would print garbage on your screen instead of the real message. And so in real life, you have to synchronize both the characters and you have to synchronize the bits. And radio teletype, you know, it actually has that feature, you know, the character synchronization built in, and they use a start bit and they use a stop bit. And the tricky thing with radio teletype is that it uses sometimes 1.5 stop bits and sometimes 2 stop bits, okay? And it's possible there are some implementations out there that use, you know, something between 1.5 and 2, okay? And so that's one of the issues that makes actual real-world decoding a little more difficult. If you notice here, here's the table with the characters, and there's on the right-hand side are the bit signals for this cheesy example here. And here's what happens with our cheesy example. If you look at it here, we've got the uncorrupted signal there in blue that we sent for the 0001, and then you'll see the corrupted signal in pink. And you notice that the corrupted signal is a lot harder to recognize than, of course, the original signal. And you'll also notice that it's delayed. Now, so the next thing to notice here is what we do in order to try and decode these things. And this idea came from, at least the earliest place I noticed it came from was Claude Shannon, who in his paper in 1948 that started this whole information theory business, he talked about a way of, in those days, of course, they didn't have computers. Well, they did, but it wasn't quite like today, you know, and A to D converters and bits and those kind of terms weren't as well known. But what he suggested doing is what we just do automatically every day now with our computers. And basically what we do is we make periodic measurements of the signal. You put the output of your radio speaker into your sound card, and your sound card measures that signal at 8,000 times a second or whatever sampling rate you have selected, okay? And so what happens is we take that analog signal, which is a continuous signal, a thing like the blue signal or the pink signal there, not the triangles and not the circles, and we turn it into something which is those numbers, which are the triangles or the circles. Okay? And so what we have done is we've taken this infinite amount of information that is encoded in the pink line or the blue line and turned it into hopefully the same amount of information in the triangles or the circles. And you know, if that was an arbitrary function, I guess there would be an infinite amount of information. But since it's not an arbitrary function, in other words, this has got to be a band-limited signal and some other things here, it probably isn't an infinite amount of information. So hopefully those little triangle numbers can represent our actual signal. And it has been shown that you can do that as long as you sample at least twice as fast as the highest frequency component in your signal. And so if you sample, an audio signal which has a 20,000 hertz bandwidth and you're sampling at 44,000 hertz like they do for CDs, everything works great, okay? And so we're going to assume that we're sampling that fast. And so what we do is we take this analog signal and we turn it into these numbers here. Now, looking at those numbers that way on the screen, as a function of time, like you would on your oscilloscope, this is your digital oscilloscope does exactly the same thing and displays it just like that. Looking at that is one way, but there's a much better way as far as communication systems and trying to recognize the signal of looking at that same data. And this better way is to take that data that's there and turn it into what's known a mathematical thing called a vector. And so I want to talk a little bit about that. Basically say we're trying to get this missing information here. Let's look at vectors. So a vector, if you can remember back from your high school math class or maybe your college math class, a vector is a thing like this. Look at the vector A there, and it has direction and it has a length. And one way of looking at that vector A is that it goes a certain amount up and a certain amount over. Do you see that? There's an x component of A, which is going over, and there's the y component of A, which is going up. And so if we just had two numbers, we could look at those two numbers, one being the x component of A and the other being the y component of A, and we could look at two numbers as being a vector. And if we wanted to find the x component of A, we would do what's known as the dot product or the inner product of A with a little vector, a vector that's 1 unit long and pointing in the x direction. So in order to find the component of a vector A in a certain direction, you do what's called an inner product. And basically what you do is you multiply the component of A in the x direction with the component of the other vector in the x direction, and then you multiply the component of A in the y direction with the component of the other vector in the y direction, and you add those two things up. And that's what's known as the inner product or the dot product. And if I wanted to use this inner product to find the projection of A onto B, in other words, how much is B like A, I would use this same inner product. Okay? It gives me the part of A that is in the direction of B. And now if we start thinking about these signals, if we take this vector idea and instead of having 2 dimensions, maybe our signal has, each of those triangular points, each one of those represents a dimension. And so now instead of being in 2 dimensions, we have a whole lot of dimensions. In other words, we've got, if we looked back at the signal here, if you look at this thing, I don't know how many triangles there are there, but for each triangle, there is a dimension. And the vector we're talking about has you take the first triangle, which is maybe over here on the left, this triangle right here. Notice that's at minus about 0.75 or something. That would be the component of this vector in the first dimension. And then the next triangle, which might be this one right here, it's a little bit higher than that, maybe minus 0.7. That would be the next component of this vector, okay? And so this vector has quite a number of dimensions. I couldn't actually show you it on the screen because we only live in 3 dimensions. And the screen is only 2 dimensions. But you can kind of generalize the same idea and think of this thing as a very large vector, okay? So let me take just a minute and stop and see if there are questions. Does this idea of a vector make sense? Maybe. Okay, so we now have this vector, which is a very large number of numbers. And generally, when we write a vector, you kind of separate them with little commas and put them in a big, a long list. And that's the vector. And we have this thing called a dot product, or an inner product, which we talked about down here. And this inner product allows us to find the component of a vector that's in the direction of another vector, okay? So let's go back up here. Let's go back to the signals we were looking at. You see these signals, the red and the blue here? We can make those into vectors as well. Can you see how to do that with the little triangles and the little circles? And you could make yourself a vector with each one of those signals. So now we have a vector for the signals we're looking for, and we have a vector for the signals we received. Does that make sense? And we have a method of finding what component of one vector there is in another vector. In other words, are they pointing in the same direction? How much are they pointing in the same direction? Or what is the part of this vector that points in a direction of another vector? So what we want to do here is we want to take and we want to do dot products or inner products of these vectors for the signals with the vectors for what we receive. The signals S1 being the one for receiving a 1 and S0 being the signal for receiving a 0. So that's the mathematical operation we want to do. Now, it's a little bit tricky because if you notice, these signals right here have a lot fewer little triangles in them than the ones we were receiving, right? So let's look at that for just a second here. Notice there are a lot of triangles on this page, whereas on the last page there were just a few. Well, here's what we're going to do. To solve the synchronization issue, we're going to take and we're going to slide those little sine and cosine vectors right here, the little blue and the little red triangles. We're going to slide those signals along this signal right here. Just slide them from the left to the right and keep doing the inner product with the small number of dimensions that we have. And we're kind of trying to match where do those two signals match. And when we slide them over so that those two vectors line up very nicely, the inner product will give me a very big number. And when they don't line up nicely, then I will get a small number. Okay? Does that make sense? So I have a measure of how well they match. And I can slide one vector along until they match the other vector, and maybe that might be where I want to start synchronizing. And once I am in sync, once I know when the first bit is, then I know when the second bit is, and the third bit, and so on. Does that make sense? And so once I know that information, I can use that inner product, that dot product again, to find out whether it was an S0 that was sent for a 0, the signal for a 0, or if it was an S1, the signal for a 1. Okay? So let's stop for a second. Are there questions about that hand-waving business?
In your example, A would be, for instance, the pink, the raw coming in. B could be the blue, the standard, what we know it ought to look like, and then you're just doing comparisons. and sliding. Is this the idea?
Well, actually, B is, or the blue there is what the transmitter sent. And the pink is that same signal, the blue thing, that the transmitter sent. And if you notice on the blue, there's kind of a low frequency. You see 2 low frequency bumps, and then you see a high frequency thing here, right? Down at the end where there's many bumps per second on the blue. That's that same 0, 0, 1 that we were looking at back here. It's just maybe a little harder to see. Notice the 0 on this thing right here is the first cycle there. The next 0 is the second cycle, and the 1 is the last 2 cycles where it went up and down really quickly. Okay, so that is the thing that was sent, and the pink is like this noisy signal over here on the right. If you look right here, the pink, this is the noisy signal. This is actually the same thing as the pink on that graph you were asking about. And so what's happening is we're going to take just a signal that looks just like this first 0 right here, and we're going to put it on top of this first 0 over here and slide it along until it matches. And if we slide it along about half a period, just about half a t there, we'll notice that, oh, it starts looking, it's right in time with that other guy. And so when we do the inner product or the dot product there, we'll get a big number in that position. Does that answer your question? Sorta. Okay, so when we slide those one vector along the other, you can just, if you think about this, just this first cycle right here, if I just took that first cycle right there and clipped it out and moved it over here, when I put it, it would kind of go up like this and then down like this, and it would come, back up right about here at T. And so it wouldn't match that one you got right there. But if I slid it over just a little bit, moved it over to the right, delayed it by about half a time T, and did the same thing, it would match very nicely. And when it matches, when you do that mathematical operation, that inner product thing, which is actually just multiplying each of those numbers together and adding them all up. It's a very simple mathematical thing to do. When you do that, when it matches, you get a really big number. And when you do it, when it doesn't match, you don't get a big number. And so when you get a big number, you've hit the jackpot. You've found the thing you're looking for. So we're using these vector ideas here, and we're trying to solve the synchronization problem. And we're trying to use the information that we have about the signal before it was sent to maximize our probability of getting the right signal that was sent, given what was sent before. Okay, so this process of doing this vector dot product is known in engineering circles as making what's known as a matched filter. Okay, it's a matched filter. And you can also do it in analog electronics. You can make a matched filter that actually, in effect, does this inner product thing for you. But once you have it in a digital form, it's very simply just an inner product, just a dot product with vectors. And matched filters are known to be optimum, the optimum filter for finding one signal in the presence of noise. And so it's an optimum filter. And one of the cool things that we do in our class, when you have these engineering students and they like elegant mathematics, we get to show that and derive that, and that's a really fun thing to do. But that's not what we want to do here. You just need to understand that that's the optimum or the best. It's the best filter you could possibly come up with. And so if you know that, and then if you implement it, your program that uses that should be the best, right? So we should be able to beat out what FL Digi was doing before, assuming they weren't using a matched filter already, and they weren't. So anyway, let's see. The synchronization problem, when do the signals start and stop? You've seen that. And we use this sliding signal, moving by, trying to get the place where it matches. And it turns out the synchronization, like I said, was the more difficult problem to solve. It was the most difficult software-wise, this sliding along and looking for where it matches. And Mark will show you some pictures of the signal after the filter process, and when you got noise on there, it's pretty difficult. Okay, so let's see. I want to look at some of the problems you have when you have to figure out how to incorporate the knowledge you have of the probabilities of the characters in the English language. How do you use that information to determine what the best, how do you incorporate that into your FLDigi program? And it's based on a theorem in probability called Bayes' rule. And Bay was actually a preacher in England back in the early days, and he came up with this rule. And you can kind of see how it works here. It's pretty simple if you are mathematically inclined. Let's just look at this for just a second. If I say one thing and another thing, that's the same thing as I could reverse the order of those two and say the second thing or the first thing, right? And so the probability that z equals z0 and something else s1, which is what I'm going to say is the signal for a 1 was sent, is the same thing for the probability a signal 1 was sent and z equals z0. And the z equals z0 is actually what I'm receiving, okay? So you kind of think about this. The probability I receive a z0 and an s1 was sent is the same thing as the probability an s1 was sent and I receive a z0. And then what we really need to do is translate this into conditional probabilities. The probability that I get a z equals z0 given an s1 was sent, or the probability that an s1 was sent given I got a z equals z0. Okay, those are the things that I need to think about instead of this one and that one. But these conditional probabilities, the definition of them here is the probability of z equals z0 and s1 is equal to the probability of S1 times the probability z equals z0 given S1, okay? And if you reverse that the other way around, you can do the same thing by using the definition. And then if you set those two things equal to each other here, up here they're equal, so this guy here equals that guy there, so this right-hand side has to equal that right-hand side. And so you got this right-hand side equals that right-hand side, and you can solve for either the probability that an S1 was sent given a Z0 was received, or the probability an S0 was sent given a Z0 was received, just by placing S0 in there. And you could also switch that around and solve for the probability, the other way around as well. You could solve for the probability that z equals z0 given an S1 was sent. So anyway, this is Bayes' rule, and it's the thing that you use to try and incorporate those things, because we want to know what the probability in S1 was sent given we received something, because we're going to be receiving something, so we know that. And that's why we needed to solve for that in order to solve this problem. So let's think about what we receive. Now remember that inner product thing that I was talking about? That gives me one number, and the one number it gives me the number which tells me how well the signal matches an S1 or how well it matches an S0. So what I do is I subtract those two numbers, and if I get a really negative number, then that would tell me a 0 was sent, and if I get a really positive number, that would tell me a 1 was sent. And this z that I'm talking about is the difference between the inner products between an S0 and an S1. So now I have one number. If it's negative, a certain negative number, that means it was likely that it was a 0 was sent, and if it's a positive number, it's likely it was a 1 that was sent. And if there was no noise present, if I could just turn off the noise, which you can in the computer when you're simulating things, then what would happen is I would have a target value that would be the inner product of a perfect signal, S1 with S1, and another target value, let's see, S1 with a difference. Like maybe I'd get -1 when it was perfectly a 0, and I'd get a +1 when it was perfectly a 1 for this one number. But what happens when I add noise into that situation? Well, let's just think about if I took off the signals, I didn't send S0 or S1, and I just sent noise through the receiver and see what would happen. Well, if I just sent noise through the receiver, generally noise, it depends on how it was generated, but in many cases noise is limited by the amount of power available from the noise source that makes it. And it turns out that if the only thing that limits it is the amount of power that's available, it's often additive white Gaussian noise, which is, it sounds like white shh kind of stuff, kind of like a little bit like QRN from the power lines, okay? And so if you can have whatever kind of noise it was, suppose it was that kind of noise or some other kind of noise, you would have that noise coming through the receiver, and if you looked at what you would get, for the Z number, it would vary. Sometimes the noise would be one way and it would give you something a little less than 0, and sometimes the noise would be something else and give you a little greater than 0. But in general, it would give you something that was kind of oscillating around 0. It would be something that on the average was 0. Because noise has the property that most of the time, its average is right around 0. It's half the time up, half the time down. And so if you looked at the noise you'd getting in, you'd see something like this little graph right here. If you graphed over and over again what you got, most of the time, 0 would be the most likely thing, and once in a while you get something down here around -1, and once in a while something around +1. But in general, if you did it over and over again, you kind of get a probability density function like that. Now, if we take the two processes and add them together, the two things are happening simultaneously, then you get this probability density function you see here, and it's centered around each of those 2 points. 1 at 1, you'd have that probability density function centered around 1, and then another one, you'd have one centered around 0 if you sent a 0 instead. So whichever one you sent, it would just move that density function. Instead of being centered around 0, it would now be centered around 1 or -1, those two target values. And so that gives you a little bit of an idea what you might expect to get. So let's kind of put these two things together, and this is the equations that go with what I've just kind of been waving my arms about. Here, this is the conditional probability density function on the top here. This is the conditional probability of whatever the number Z would be, which is what my dot product gives me. It would be just that same noise density function shifted over around 1, or -1 in this case, I guess, because A0 is -1, and A1 is 1 if it was S1 was sent. And so then you use that Bayes rule that I just went through, and the definition of the probability of Z equals Z0 given S1, and the probability Z equals Z0 given S0 here, these two definitions, and the Bayes rule, and you put it together and you get the probability that an S0 was sent given we received this specific value Z0. And you can also do the same thing for the probability of S1 given that you received a special Z0. And if you look at a picture of that, well, before I do, look at the bottom. The denominator of this equation is the same as the denominator of that equation. And so if I compare the two, I want to figure out which one of those two is the biggest one, right? And that's what I want to say was sent. Once I receive something, I want to pick the one with the biggest probability of that thing being sent given what I was received. So I want to pick the one that's the biggest, and they both have the same thing in the denominator. So I only really need to look at the numerator. And so that's this thing on the top, which is that density function scaled by the original probability that an S0 happens. And that's the original probability, that you're going to send a 0. And that's what we call the a priori probability. And this thing right here is the a posteriori probability. The left-hand side, this whole thing is the a posteriori probability. That's the thing after the fact. Okay, so here's a little picture of that. Notice the little hump on the left here. That's because a 0, in this case, was not as likely as a 1. Okay? Whatever system this is, it doesn't send zeros as often as it does a 1. And so you can see this is bigger. And so if we got a point, say if we got a minus 0.01 here, we would say that, oh, it's probably right here, and this one right here is bigger than that one, so I'd still say it was a 1, even though it was negative, okay? Now, there's another kind of detector that doesn't use these a priori probabilities that would just say, oh, if it's less than 0, we're going to say it's a 0, and if it's greater than 0, we're going to say it's a 1. That's called the maximum likelihood detector, and that assumes the probability of a 0 is equal to the probability of a 1. And so this detector, that's not what we want to do for our detector. We want to assume that the probability of E is greater than the probability of an X. And the difficulty now is to take these ideas that we've just done in one bit, one dimension, and translate those to 2 dimensions, or many dimensions, because our characters actually have several dimensions. But if you can understand how to do it to 2 dimensions, then going to higher dimensions is not terribly difficult, okay? So let's quickly look. Here's what the noise density function looks like in 2 dimensions. It's just a hill. And here's what happens to that last graph if you look in 2 dimensions. Notice there's several hills, and you would get a certain number on that plane there for getting 2 bits. One in the first bit direction and one in the second bit direction. And you'd get that number, and you would look at which hill is the highest at that number. And that's the bit you would decode. Okay, so I'm going to let Mark take over here and show you the real results, because that's where the excitement is all at.
Now for the fun part. Basically, this is the first thing we had to do was generate a clean radio teletype signal so that we could test our software off of. And this is what comes out of the matched filter once you run it through the dot products and everything. And basically what you're seeing here is a transition between a 1 to a 0 bit. The red there is the output from the one matched filter that looks at the lower frequency, I believe it's the lower frequency for the 0 bit, and the other one is for the 1 bit. And so you can clearly see here with no noise a signal transition between a 0 and a 1. And we have to synchronize right at the peak here, so we had to write an algorithm that would tell our software to sample right at this point and say, this is our sample point. After that, we decided we'd run it through a program to generate a bunch of noise. And this is the same signal at about negative 6 dB signal-to-noise ratio. And it's mostly the same. However, we have a lot more issues with false positives, because like right around in here, it's tough to know whether you have a transition between a 0 and 1, or whether it's supposed to stay 0, but the noise bumped the one over the other. So we had to add on top of our synchronization filter an averaging filter because for the sync points, because we know that each bit comes at exactly, well, since it's this case it's 45 baud, we know exactly when the next bit is supposed to come, so we can always sample there, and then the timing differences will get consumed in the average and will eventually converge onto where it's supposed to be. We just grabbed the first page of our paper and calculated some probabilities for each letter and ran it through our program. And basically found that it corrected 84 letters. 46 was a correct change, and 38 it actually changed a right letter to an incorrect letter. But overall, that's still a 9.5 improvement over the maximum likelihood. And for the really cool stuff here, I can show you a demonstration of what all this means here. Basically, on the left is the original nonlinear before the matched filter, and on the right is our a posteriori after a matched filter. The biggest improvement is actually from the matched filter, but as you can tell, there's actually quite a difference. The left is basically gibberish, and then once you run it through the matched filter and the a posteriori probabilities, you can actually read it. So this basically extends your effective range by quite a bit, because now you can read signals that you previously couldn't read. Any questions?
So have you done 2 things here? You've done the matched filter and you've done the
A posteriori.
A posteriori.
Yeah, to incorporate the English language. That gave you about a 10% better, but the matched filter actually made a much bigger difference in this case.
That's what I would expect, and I'm actually more interested in how much you get from the unpronounceable word, the a posteriori. Can you phrase, you had something in there that said some percentage improvement, but can you tell me how much of an improvement that would be in And how many dB weaker can the signal be, and I still get...
Yeah, well, I haven't tested that. It's a good question. I haven't really...
Is it even a tenth of a dB? That's why I'm a little skeptical.
Yeah, I don't know how
that.
much better that you can turn it down. But if you, it's changing 10% of the changes it does. Are better than it would have if it wasn't run. So the maximum likelihood detector is going to have about 10% more errors than a maximum a priori or a posteriori detector. So that's about. I mean, so if you can just say in terms of the errors, we can give you the answer. But we haven't tried it. We could run some tests, and we could do this in the demo room and change the the signal-to-noise ratio. This signal-to-noise ratio is about -6 dB at this point, what we're using right here. So we could run another one at -6.5 dB and run one without the a posteriori and one with it and see if it was the same, but we haven't done that.
Have you done this with PSK instead of a teletype? A PSK 31 in particular?
No, not yet. A lot of the code is the same, but the gain in PSK, at least for the a posteriori detector, would not be as great because PSK 31 already takes into account that an E is more likely than an X because it's a shorter symbol. So does Morse code, for that matter. But the matched filter, I don't know. We haven't really looked at the code in FLDigi whether they're using a matched filter. The matched filter might improve the PSK demodulation in a similar way as it did here. I don't know. We haven't looked at that yet.
Okay, one more question.
This may overlap with the first question a little bit, but I was wondering if the usable signal-to-noise range that you could do the match filter effectively was different than the signal-to-noise you could tolerate with the a posteriori filter.
It should be slightly better with the a posteriori, but the a posteriori requires the matched filter. In other words, we couldn't just add the a posteriori stuff into the original FLDigi demodulator because it's a nonlinear demodulator, and our theory that I just described is all based on linear things. In other words, the noise is added to the signal. And so the result is the result of what we would get with just the noise plus the result with the signal. With the regular FSK detector, when you turn on your HT and you just listen, when nobody's talking, you get a terrible noise out there. And the output when somebody's talking is not that terrible noise plus what was talking because it's a nonlinear detector.
Okay, well, that's all we have time for. Thank you very much.